Hello everyone, welcome back to this week's seminar. Today Alexey will tell us about the combinatorial Nullstellensatz and the Erdős box problem. Alexey.
Hello everyone. Yeah, thank you for inviting me to this seminar. So as you can see, there are two topics in the title. So the talk will be organized as follows. I would first have the two introductory parts. So I'll talk about combinatorial Nullstellensatz and how it's usually used in combinatorics, and talk about a particular version which I will be using in this talk. Then I'll talk about Turán numbers of graphs and hypergraphs, and define the Erdős box problem and tell you what people know, what people don't know about this particular problem. And then I would talk about how these two topics are connected and how this connection can be useful. Great. So if you, the topic should be fairly simple. The talk should be fairly simple. I will, in fact, hope to give you the whole proof of my construction, and it should be very simple, just like 2 slides. So if at any point you have any questions, please stop me and ask questions. We should have ample time to discuss everything. All right. So let me start by defining combinatorial Nullstellensatz. So this is one of examples of what's known as polynomial method in combinatorics. Let me first define the theorem, and then I will talk about how people usually employ it to prove results. So suppose you have some field, any field. Suppose you have a polynomial over several variables in this field. By the way, can you see my mouse pointer when I move it, or can't you? Oh, great. Great. So suppose you have a polynomial f over several r variables. Throughout the talk, r would always be some constant. So it's, yes, it's always fixed. And by square brackets, I would denote the coefficient which some monomial has in polynomial f. So this is if you write an expansion of f, then this monomial appears with some coefficient. That's how I denote this coefficient. So the combinatorial Nullstellensatz was proved in the paper by the same name by Alon in 1999, but in fact, this kind of tool was used throughout the 90s to obtain several results in combinatorics. And in this paper, Alon just kind of crystallized it into this abstract lemma, which you can use in different contexts. So what does it say? It says that suppose you have some polynomial and you have fix any monomial of the highest degree in this polynomial f. So degree of f is the same as degree of this monomial in f, which has non-zero coefficient. Then, so I have like a formal statement here and a bit less formal, but maybe more readable statement here. So the idea is that polynomial f cannot vanish on any sufficiently large product set. If for every variable we choose any subset of values of size at least degree of this variable in monomial plus 1, then on the resulting product set, a1 times and so on times ar, you can always find a point at which polynomial is non-zero. Or in other words, the polynomial cannot completely vanish on any such product set. Yeah, so this can be maybe a little bit overwhelming. There are a lot of concepts here, so I will try to first give you a very simple illustration, and then we will try to prove some, to give some classic application of this theorem. Yeah, so let's consider kind of the simplest example. Suppose we have just 2 variables, and suppose our polynomials, suppose we fix the degree of polynomial as 4, and we fix this monomial with non-zero coefficient to be x square y square. So now we can consider any polynomial of degree at most 4, of degree 4, which has this x square y square with some non-zero coefficient. And so the theorem says that we can choose any grid, finite grid of points on the plane, which has at least 3 values for x and at least 3 values for y. So in particular, we can fix this grid, right, which you can see on the picture. So what the theorem says is that if your polynomial has this form, it can never completely vanish on this grid. It would always have at least, it will always be non-zero at least on one point of this grid. So, and in fact, we can like consider several examples. Example, we can like draw two vertical horizontal lines and fix and kind of cover all points except one on this grid, right? So this is polynomial of degree 4, in which this coefficient is, which monomial has non-zero coefficient, and it covers almost all points. But the theorem says that such polynomial cannot cover all the points. Or we can consider a product of two equations for circles, and this would also be polynomial of this form. It again covers some points, but it cannot cover all the points. So that's the point of the theorem, that polynomials of this form, they cannot cover any sufficiently large multidimensional grid or product set. So it may be unclear how this can be useful to prove some combinatorial results. So let me give you like the simplest way to kind of try and give you an intuition about how it's usually used is just to prove, to give a classic application. Let's just prove Cauchy-Davenport theorem, like the first theorem in additive combinatorics. So what is Cauchy-Davenport theorem? Suppose we have some prime P, and we have two non-empty sets, subsets of ZP, so of remainders modulo P. Then there some set A plus B, which is just the set of all possible sums of an element from A plus an element from B, cannot be too small. It always has size at least A plus size of A plus size of B minus 1. Oh, but you have to take minimum with P because, of course, the whole ZP is just P elements. So let's prove it with our combinatorial Nullstellensatz. The first thing is we kind of have to consider an edge case. If sets A and B together are already big, if sum of the sizes is greater than P, then we don't need any powerful tool. We can just use pigeonhole principle, because we can take any remainder modulo P and see that by pigeonhole principle, A and this remainder minus B, these are two sets which together have more than P elements. So by pigeonhole principle, they have some common element. But this just means that if you take this common element, it corresponds to an element of A and an element of X minus B. So it just means that X belongs to A plus B. And since we showed it for every X, it just means that A plus B is the whole ZP. So this is an interesting case. Now let's consider the opposite case, and let's suppose the theorem is not correct. So the sum set is of size less than A plus B minus 1. So it's of size at most A plus B minus 2, which in particular is less than P because we are already considered then the sum of A and B is large. So how do we employ combinatorial Nullstellensatz here? We consider the following polynomial. For every element of our sum set A plus B, we multiply a linear factor X plus Y minus C for variables X and Y. So why is this polynomial useful? It's useful because if we substitute any element of the set A for X and any element of a set Y, of a set B for Y, we would always get 0, right? Because A plus B is some element of the sum set, and then one of the factors would be 0, just by definition. So this polynomial vanishes on the product set of A and B. But now we can say that, in fact, by combinatorial Nullstellensatz, it cannot vanish on this product set. Why is that so? Because let us look at this particular monomial in this polynomial. So suppose we want to see the coefficient of monomial which has X with degree size of A minus 1 and Y with this expression, which is just degree of F minus the degree of X in this monomial, right? So what is the coefficient of this monomial in F? To get this monomial, we should take either x or y from every linear factor, right? If we take a constant, then we would not get the maximum degree. And that just means that this coefficient is just a binomial coefficient of the size of some set, choose size of a minus 1. Since by our assumption, size of some set is less than p, this coefficient is non-zero modulo p. So we can apply our theorem. And our theorem says that the polynomial f cannot vanish on any sufficiently large product set. And on the product set which has greater than this many options for x and greater than this many options for y. In particular, the product set a times b is our theorem is applicable to it. So we get a contradiction. On the one hand, clearly this polynomial must vanish on our product set. On the other hand, it cannot vanish by combinatorial Nullstellensatz. Okay, so are there any questions up to this point? Okay, so this is kind of how this theorem is usually used. So you have some object which you are interested in. You interpret it somehow as a zero set of some polynomial, and then you employ combinatorial Nullstellensatz to get some structure on the zero set of this polynomial. This gives you information about the object you were studying. So in this case, the structure is just the lower bound on the size of the object. Yeah, so we were interested in our sum set, and we just showed that it cannot be too small. But in the application that I would talk about later, this would be like more refined structure. It would be more interesting. Okay, but actually we would not use this combinatorial Nullstellensatz. We would need a stronger theorem. So this is again the statement of Alon's theorem, but in fact you can show that a stronger theorem holds, and Lasoń showed it in 2010, that instead of this condition, instead of asking for this monomial to be the monomial of highest degree in F, you can just ask for this monomial to be maximal in F. The maximal just means that it appears in F, it has non-zero coefficient, and no other monomial divides this monomial. And if this monomial is maximal in F, then the same conclusion holds. So as an example, we can look at the polynomial x to the 100 plus xy plus y to the 100. And here xy is a maximal monomial because none of these two divide xy, because each of them doesn't contain either x or y. But on the other hand, the degree of xy is just 2, but the degree of polynomial is 100. So this theorem, Lasoń's theorem, is indeed much stronger. And this is the version of combinatorial Nullstellensatz which we will be using later. So two things to note here. The first is that, in fact, around the same time, Schaus proved an even more general theorem, which is would take longer to state. So I won't be doing it here because we don't really need a stronger statement here. And the other interesting point is that for some reason, in basically all applications of combinatorial Nullstellensatz, at least those that I know of, the classical Alon's condition, where you just want to have a condition on the degree of polynomial, it's for some reason sufficient. So usually then you encode your object as polynomial. It either turns out to be a homogeneous polynomial, so all monomials have the same degree, and this stronger theorem doesn't really give you anything more. Or even if polynomial is not homogeneous, you're usually interested in monomials of highest degree. Yeah, so Lasoń in his paper gave kind of an example of the problem in which his theorem does the job, but Alon's theorem doesn't. But it was kind of a problem designed to be this way. So he just designed the problem so that his theorem works and Alon's theorem doesn't. Again, today I will give you an example of an application where you really need this stronger theorem. The classical combinatorial Nullstellensatz is kind of useless in this context, which is interesting. It would be interesting to find more applications of a stronger theorem. Okay, so that's the end of the introductory part about Nullstellensatz. So it's again a good point to ask questions if you have any. If not, we will move on to Turán numbers. Okay. Yeah, so let's talk about Turán numbers. So suppose you have a graph G, then the Turán number, or it's also called extremal number of G and N, is just maximum number of edges which you can have in a graph on n vertices such that it is G-free. G-free means that it doesn't contain G as a subgraph. So there are no subgraphs isomorphic to G. So this, of course, the study of these numbers kind of started by Turán, who proved in one his famous theorem where he, in modern terms, determined the extremal number for a clique. And he showed that this expression holds, where the extremal example, the graph on n vertices, which has the most number of edges but doesn't contain a clique on n plus 1 vertices, is just a m-partite graph with parts of roughly the same size. It's known as Turán graph. And soon after that, Erdős and Stone proved that, in fact, you can show kind of a similar formula for any graph G. Instead of 1 over m, you have to put here chromatic number of G minus 1. And the extremal example is basically the same Turán graph. So this formula is interesting in that if G is not bipartite, so if here G is greater than 2, then this basically gives the asymptotics of the extremal number. So even with the right constant, so with this constant. But if graph is bipartite, then all that this formula gives you is that extremal number is O small of n square. And you don't really know the asymptotics for order of growth in terms of n. And in fact, for a lot of bipartite graphs, this problem of determining this extremal number is still open. So two kind of large areas in which people work and have a lot of results are complete bipartite graphs and cycles, where are also some other results. But today I would focus on the case of complete bipartite graphs, because it's kind of a natural thing to do. If you don't know what to do for any bipartite graph, you can consider like the simplest bipartite graph. This is one of the definitions of the simplest. So from now on, we would talk about complete bipartite graphs, but also we would move into the context of hypergraphs. So we will talk about analogs of bipartite graphs for hypergraphs. So these are r-partite, R graphs. What is an R graph? That's just a hypergraph in which every edge has size R. So usual graphs are 2 graphs, but here we can have some fixed R. And yeah, then it's just have a way to think about is just like a family of sets of size R over some ground set V, which are vertices. And if we fix R, we can again, for any R graph H, define the Turán or extremal number of H as maximum number of edges, this time in R graph on n vertices, which doesn't contain H as a sub-hypergraph. Okay. Now, what is an r-partite R graph? This is basically an R graph in which you can split all the vertices into R parts, such that every edge intersects every part. Or what follows is that every edge contains exactly one vertex from every part, right? So for R equals 2, you just get bipartite graphs. For larger R, you get like this generalization, r-partite R graphs. So you can kind of think about it this way. You have R parts, and every edge has like one element from every part. And the complete r-partite R graph with parts of size S1 and so on as R is just when you have all possible edges. So it has S1 times and so on as R edges, every edge which you can draw here. Okay, so now we kind of would focus on the problem of determining the asymptotics of extremal number for complete r-partite R graphs. But before talking about like the history of this problem, I want to maybe foreshadow the connection which we will use because if you remember, we started by talking about combinatorial Nullstellensatz and zero sets of polynomials. Particularly, we had product sets where I want to show you another way to look at on r-partite graphs, which maybe like suggest what we will be doing later. So if we have complete bipartite graph with S vertices in one part, T vertices in another part, we can draw it in this way. We can draw S horizontal lines, T vertical lines, and say that every edge corresponds to an intersection of some vertical line, some horizontal line. So in this sense, complete bipartite graphs are just product sets on the plane. And similarly, for r-partite graphs, you can look at them as these product sets in r-dimensional space, where you again fix some set v1 of values for the first coordinate, v2 set v2 for values of the second coordinate, and so on. And then you just look at this product set, and any r-partite graph is some subset of this large product set, and the whole product set is the complete r-partite graph. Okay. So what do people know about the Turán numbers of these complete r-partite graphs? In 1964, Erdős proved the following bound, which extended the bound for graphs by Gordeev, Turán 10 years earlier. That you can you can show that the maximum number of edges in the hypergraph free of these subgraphs is definitely smaller than n to the r, and what you can subtract from n to the r is 1 over the product of all parts except the largest part. Then, like, his proof is basically for any subset of r-1 of these r values is just like this is the best bound when you take the r-1 smallest ones. Okay, so this bound was proved in 1964, and since then there has been no improvements of the upper bound, and it was, I think, widely believed and then formally conjectured by Mubai in his paper of 2002 that this bound is asymptotically tight for all parameters. So when is this conjecture known to be true? It's known it's true for in the graph case, so when r is equal to for k22 and k33. And this there are matching lower bound constructions, so just examples of a series of graphs which don't contain k22 or k33 as subgraphs and which have a lot of edges. The first one was done by Esther Clay in 1934. This kind of seems to be the first extremal construction which uses like finite geometry, the first algebraic extremal construction of this kind. And also a similar algebraic construction was done by Brown in 1966. And yeah, the only other case where conjecture is known to be true is when the last part is much, much larger than all the other parts. So this bound is in terms of SR should be at least the product of all the other sizes of all other parts factorial plus some function of factorial of a product of sizes from all other parts. So it's like much larger than all the other parts combined. And this has been done in the 90s for graphs, basically when S2 is much larger than S1, in a series of works by Alon, Kohler, Renier, Jabo. And recently it was generalized to hypergraphs by Pohuat and Zakharov. And the construction in this case is, again, algebraic in nature. And interestingly, there is, again, a series of papers which started, again, for graphs by Blagojevich, Buch, Karashev, and then improved by Buch, what's called as random algebraic method. And this was also recently generalized to hypergraphs. And this, it's interesting that like there are two quite different proofs which prove the same theorem, but I think here bound is a little bit worse in terms of how much SR should be in terms of all the other parameters. But this method combines some algebraic structure with some probabilistic arguments. And it's interesting that it gives like a tight bound asymptotically, because usually probabilistic arguments here in extremal in this setting give some bounds which are far from the best upper bound people know. Okay. So now let me talk about the Erdős box problem. And this is just a particular subcase of the problem of determining these Turán numbers. Then all these asides are equal to 2. So why is it called an Erdős box problem? Because you can think about it this way. You have this n times n times n times n big product set, so a big r-dimensional box. And you want to choose as many points in this product set as possible so that no subset of points forms a 2 by 2 by 2 by 2 box. So this is why it's kind of called Erdős box. Yeah, so your forbidden hypergraph in this case is just a set, like in this, if we draw pictures like that, then this is just basically a set of vertices of r-dimensional cube. But these vertices are in fact edges of hypergraph, which may be confusing. Okay. Yeah, so the same Erdős bound in this case turns out to look like that. And again, people don't know how to improve it. The only case when there is a matching lower bound is again the construction Westerklein for k to 2, and for r greater than 2 there are no matching lower bounds. So what do people know? For r equals 3, there is construction by Katskrop-Meggioni, which is also some like algebraic construction using finite fields. And the current state of art result is by Konlon-Pohat-Zakharov a few years ago, who improved an earlier paper of Gurdenson, Rodli, Sidorenko, who in turn improved like the basic probabilistic argument that you can do. And it looks quite complicated, but if you remove the ceiling function here, then you would get the bound which you can get just by applying the simplest probabilistic argument. So they kind of improved it a bit by adding a ceiling function here. And again, the proof combines some algebraic structure and some probabilistic arguments. Okay, so now we're ready to talk about what I'm going to show you today. And I will show you a bound which is maybe a bit less exciting. It's just r minus 1 over r. But I think this bound is still interesting, first of all, because it's kind of just an illustration of what I hope is a more general method, which uses combinatorial Nullstellensatz. And the other thing is that construction is explicit. So for now, it doesn't use any probabilistic arguments. It just, I can just show you that a series of hypergraphs, which you can construct explicitly. And the proof is very simple. Again, I hope to show you it's in its entirety. Okay, so we can write down the values of these functions for small r, and for r up to 4, this construction actually has the same asymptotically size as the best known construction. For great R, it kind of falls off, but for some period of time, I was pretty sure that for r equals 4, this is the first example of, again, explicit non-probabilistic construction of this size. When I was preparing the paper, I actually found out that there was a recent PhD thesis where was offered claims to extend the construction of Katskrop-Meggioni to give the same bound. And his construction also seems to be deterministic, but the proof is much more complicated. It's like close to 10 pages, I think, of calculations. Yeah, and I will maybe talk about that at the end, but it seems that these constructions are structurally very similar to one that I'm about to give. They just like the proof is different. Okay. Yeah, so now let me finally talk about how these two topics are connected. How can we connect Turán numbers of complete r-partite R graphs to combinatorial Nullstellensatz? And yeah, the connection is actually surprisingly simple. I should mention that it was this framework I'm about to give was described in very similar way, but maybe with slightly different emphasis in the recent survey by Rota. Yeah, and what's surprising is that seems to be the first written work where I saw this connection, even though, as we will see, it's really simple. We just have to restate Lasoņ's theorem in terms of hypergraphs, and we will immediately get the result that we need. Yeah, but for some reason, it looks like people didn't notice it until recently. And this survey is kind of motivation if I write down my construction. Okay, so let me set up our setting. We again have a field. We have a polynomial in our variables. And suppose we fix some product set B. For now, it's just any product set. So we just fix some set of values for every variable. We can define Z of FB as just the zero set of F on this product set. So the subset of points on which polynomial is zero. And again, the key thing is we can view this zero set as an r-partite R graph, because we can say that these sets B1, BR are our parts, and 0 points of polynomial are edges of this hypergraph. So every zero set of polynomial is, in a very natural way, corresponds to an r-partite R graph. So if we look again at the polynomial, which is a product of two circle equations, and on this 3x3 grid, then it would correspond to a bar-partite graph in which both parts have 3 vertices, right? Because we have 3 values for x and for y, and there are 7 edges. And in general, again, we have some subset of the product set of multidimensional grid. Okay, so for now, we didn't do anything. We just said that we can look at zero set as a hypergraph. So now let's remember Lasoņ's theorem. It says that if we have some maximal monomial in our polynomial f, when for any sufficiently large product set, A1, so on, times AR, we could always find a non-zero point on this product set. So first of all, instead of taking any A1 and so on AR, we can take subsets of our fixed product set B. So for now, I just restricted the theorem to like, I just restricted the possibilities for the sets II. So of course, the theorem is still true. But what does it mean now? So we have our big r-partite graph H of F and B. And what the theorem of Lasoń says is that if we take a subgraph H of FA for any product set A in which the part II has size at least di plus 1, we would always find a non-zero point. What this means in terms of hypergraph, it just means that HFB is free of this kind of ordered copies of the complete r-partite graph with d1 plus 1 vertices in the first part, d2 plus 1 vertices in the second part, and so on, dr plus 1 vertices in the last part. What I mean by ordered here is, again, that we want to have, we are free of copies of this hypergraph, which have exactly d1 plus 1 vertices in B1, d2 plus 1 vertices in B2, and so on. Yeah, right? Because that's what the theorem tells us. But from this point, it's very easy to go to just showing that H of FB is just free of all copies of some slightly large hypergraph. So if D is maximum of all di's, then H of FB is clearly would be free of all copies of this complete hypergraph, right? Because if it contained copy like that, then you could, this subhypergraph would contain a subgraph which is an ordered, this smaller complete r-partite graph. So we just restated Lasoņ's theorem in slightly different terms, in this hypergraph notation, and they got this, what I would call key lemma, is that if our polynomial has some maximal monomial, then any zero set of F would be, if viewed as a hypergraph, would be free of copies of some, again, complete r-partite graph whose parameters depend on this monomial from which we started. And if you want, maybe I would not spend a lot of time on this, but we can write it lemma in like slightly more general way. If you want to have different values here, then we just need to ask that for any permutation of indices, such monomial would be maximal, or even we can ask that some smaller monomial which divides this one would be maximal. Then we can show this thing that we wouldn't have these copies for any permutation of parts. Okay, so how can we use this lemma? One way would be the construction, which I'm about to show, but first I want to talk about the other direction. So let's recall that we have this upper bound by Erdős, that any hypergraph free of complete r-partite graph has not too many edges. And here in our lemma, we have shown that any hypergraph of a form HFB is free of copies of some fixed hypergraph. So let's just combine these two results. What we immediately get is that if our product set B has every component of size n, then on any such product set, polynomial f would have at most this many zeros. So this is a result which is very similar to Schwarz-Zippel lemma, where you have some conditions on polynomial and you bound the number of zeros on a product set in some way. But this doesn't seem to follow from any versions of Schwarz-Zippel lemma that I know of. And it's also interesting that the proof is basically graph theoretic. So for example, if we take polynomial like that, x to the n plus y to the n plus xy, then by this corollary, on any product set size n in each component, it would have at most n to the 3/2 edges. But since this is polynomial of degree n, the usual Schwarz-Zippel lemma wouldn't give any non-trivial bound on the number of zeros. And some generalization, what I know of, also wouldn't give anything non-trivial. Yeah, so I think it's an interesting corollary. I'm not sure if, I don't know of any useful applications. Again, if anyone has any ideas, that would be very interesting to discuss it. Yeah, but now, yeah, and the last thing is that actually, if we go back to Erdős proof and repeat it, we can actually show that instead of using this lemma as a black box, we can kind of combine all the steps together and show that, in fact, you can give a slightly better bound. But yeah, maybe I will not focus on that today. Yeah, so now let's talk about the construction, which I promised. So first, we have some technical lemma, which for now I want to just state and skip its proof. But we will maybe go back to the proof in 5 minutes. So the lemma is just like that. If we have this fixed polynomial, which is just product of all variables plus some kind of cyclic sum, where every other monomial is a product of some degrees of all variables except one, because here we have product of r minus 1 variables in every monomial. And yeah, here the index is a cyclic modulo r, so xr plus y is same as xy. So let's just consider this polynomial. And turns out that it has of a product set of non-zero elements of a finite field of size p to r. This polynomial has a lot of edges, a lot of zeros. What I mean by a lot of zeros, I mean that the whole size of this product set is p to r minus 1 times r. So what we lost here is basically one factor of p. So like the density of zeros in this product set is roughly 1 over p. Yeah, so let me first tell it how from this technical result we get the bound, which I promised. So this monomial is clearly maximal in F because every other monomial doesn't contain one of the variables. So clearly, this monomial cannot divide any other monomial. Then we can apply our key lemma. And since here every variable is just degree 1, we get that on any product set, in particular on this product set, this polynomial, the 0 set, when viewed as hypergraph, would be free of the Erdős boxes, or free of copies of Erdős boxes, which is exactly what we want. Yeah, what I want to emphasize is that here the classical combinatorial Nullstellensatz would be kind of useless, because if you wanted to prove a similar result using the Alon's version of Nullstellensatz, when we would kind of need to find a similar polynomial in which this monomial is also maximal, but whose degree is at most r, because this monomial has degree r. And just if you consider any polynomial of degree at most r, it, by the usual Schwarz-Zippel lemma, it wouldn't have a lot of zeros. So you wouldn't be able to get a construction like that. You really need this more powerful version of Nullstellensatz here. Okay. Yeah, but now to get the bound, which I promised, we just need to count vertices and edges. So here we have r times p to the r minus 1 vertices, and we have this many edges, which, if you restate it in terms of n, is basically n to the r minus 1 over r, with some constant which depends on r. But since r is fixed, we can hide it under omega. Yeah, so that's how we prove the construction. Since you can do it this for any prime number p, you really have a series of hypergraphs which have these many edges which don't contain an Erdős box as a subgraph. Great. So since we still have time, I want to show you the count of zeros of this polynomial, since it's actually also very simple. Yeah, so one property that we need is that any element of a finite field of size p to the r is equal to itself if you take it to the power p to the r. So let's, and that means that if we rewrite this expression in a slightly different way, if we take the product of all AIs outside and replace p to the r here with 1, then this expression would turn into this expression. And what's in the brackets here is actually just 1 plus the trace of some expression, where trace is the trace function of a field extension of fp to r over fp. It's defined like that. Yeah, what we need from the trace here is basically that it takes values in fp for every element of fp to the r, and moreover, it takes every value the same number of times. So in particular, it's equal to -1 p to the r minus 1 times when you go for non-zero elements of a field. And this just means that if you fix all elements except a1, if you fix any value of every other variable, then once you go through all values of a1, this product also goes through all non-zero elements of the field. And since there are exactly p to the r minus 1 of them for which trace is -1, there are exactly p to the r minus 1 of them for which our polynomial is 0. And this means that the total number of zeros would be the total number of choices for all the other variables, which is p to the r minus 1 to the r minus 1 times this. Yeah, so that's what I promised on the previous slide. Yeah, so it's a very simple proof. Of course, the hard part here was finding this polynomial, which had a lot of zeros. Proving that it has a lot of zeros is not that hard. Yeah, so yeah, that's the result that I want to talk about today. So let me kind of finish about possible directions of future work. So one thing is it would be, my hope is that more constructions can be found using this framework, this method. Of course, the problem here is how to find like these interesting polynomials which have a small maximal monomial but have a lot of zeros. So for this polynomial, how I found it is I kind of did a computer search for two variables in small finite fields, then noticed some symmetries, and then like I figured out how to expand it for any number of variables for any r, and but in general, it seems hard to find like interesting polynomials in this sense. So again, one hope would be to find a way to add some probabilistic arguments, maybe choose a product set somehow randomly, or choose the coefficients of polynomial in some controlled probabilistic way. Again, it just seems that all the recent state-of-art constructions, lower bounds usually combine some algebraic structure and probabilistic arguments. And here we have some algebraic structure. It would be nice to find a way to add probability to it. But I'm not sure how exactly to do that. The other thing is, as I said already, it seems that one of the earlier construction seems very structurally similar to the zero set of this polynomial, which is like I kind of found after I had these constructions. I just read this earlier paper, and it seems that I don't really know how to prove it. I didn't try to prove this formally, but it seems that like the structure is basically the same, just the proof is different. So again, it would be interesting to maybe look at other constructions and see if they can be translated into this framework, into this language of zero sets of polynomials. Because again, in this case, the proof using combinatorial Nullstellensatz is much simpler and shorter, and it's also very easily generalizes to several variables. And you just clearly see how to generalize it to several variables. So the hope would be that maybe some of our constructions would also, you could improve them by translating them into this framework. But this, again, it's an open question if you can do that. The other thing is, as I said, it would be interesting to find some applications of this corollary. And another question is, you can ask is, like, then is this corollary optimal, and when is it optimal? So here I want to kind of convince you that this whole studying this framework is an interesting problem, because so this question has one of two answers. Either this corollary is always optimal, or you can find some counterexamples, find some settings where you can get a better bound on the number of zeros. So suppose that it's optimal. This means that you can get the best constructions for Turán numbers using this framework. But there are some polynomials with large zero sets, and you just need to find them. So showing that this corollary is optimal would actually be the same as showing the lower bound or matching the Erdős's upper bound. On the other hand, if you can show that this corollary sometimes is not optimal, you can I can show like a stronger Schwarz-Zippel type results, which also seems to be interesting. Yeah, and what we know so far is my construction kind of shows that this corollary is tight, again, for r equals 2, when you consider polynomials with xy being a maximal monomial, and then your field is fp square or contains fp square. But another question you can ask is also, can you do a better bound if your field is restricted? So can you improve this upper bound, this corollary, for a particular field? In particular, Rotter, in his survey, asked the question of how large can the zero set be if you work over integers. So my construction kind of answers these questions for fp square, but for integers, it's yeah, you can't really translate it into integers. So in integers, it's still an open question. Yeah, and the last thing is that I want to, like, one of the goals of this talk is to advertise Lasoņ's version of Nullstellensatz, and if anyone can find other applications, I would be happy. So yeah, that's the end of my talk. Thank you.
Thank you for the nice talk, Alexey. Any questions? So how will you try the K33 result?
Yeah, so that's kind of my next goal is, yeah, to read the Brown's proof of the, I mean, I know it on like a high level, but I didn't really read the details. Yeah, so I want to like go through his proof and try to translate it maybe into this language. I'm not sure if it would work out, but yeah, that's the next step. It's just I'm here on kind of a completely different project about design from design theory, and just don't have a lot of time right now to work on this problem. But yeah.
So if you try for T333, the polynomial should be something like x1 square, x2 square. The monomial, they have something else.
Yeah, I think we should probably try to do it from K33 at first for just for graphs, because if in this case people actually know the. Let me get back to it. Yeah, so where is this matching lower bound from Brown, which is also actually a construction using finite fields. It's some intersections of spheres in the FP cubed, I guess, FP cubed times FP cubed. Yeah. So, and spheres are kind of two-dimensional polynomials, so I have some hope that maybe you can rephrase it, but I didn't really have time to think about it a lot. Yeah.
Yeah. Do we have other questions for Alexey? If not, let's thank Alexey for the nice talk.